In the vast cosmic tapestry where stars and galaxies shine brightly, a hidden era known as the cosmic dawn once shrouded the universe. It was a time when a veil of hydrogen atoms concealed the light from nascent stars and galaxies, veiling the universe in obscurity. It was a fierce ultraviolet radiation of the earliest stars and galaxies that, over eons, managed to pierce through this hydrogen fog, heralding the transformation into the luminous universe we witness now. In the quest to fathom these primordial realms, astronomers have long yearned for tools that could decipher the universe's enigmatic beginnings. The James Webb Space Telescope, JWST, a marvel of modern technology constructed by NASA, as well as Europe's and Canada's space agencies, has become a key instrument in this quest. This cutting-edge telescope's advanced capabilities have enabled astronomers to scrutinize the very stars and galaxies that took shape in the aftermath of the monumental Big Bang. For months, James Webb has stunned the whole world by capturing early galaxies, defying the cosmic rulebook of the early universe. And now, in the latest discovery, James Webb continues to unveil the existence of a bunch of ancient galaxies, unlocking secrets of how infant galaxies started an explosion of star formation in the very early universe. Join us today as we dig deep into how James Webb's new discoveries shed light on the early universe. Constructed by NASA, as well as Europe's and Canada's space agencies, the JWST is the most powerful off-world observatory yet built. But for a time, the observatory was more of a cruel joke among astronomers. The technical demands of its development pushed the project so far over budget and behind schedule that many suspected it would never launch at all. Despite the debates over the telescope's naming and history, one thing has become abundantly clear this year: the scientific ability of James Webb is simply remarkable. The premier observatory is already delivering on its promise to revolutionize our understanding of the cosmos during a mission that could stretch into the 2040s. The first photos from James Webb went out to the world on July 12, 2022, and they were stunners. The clarity and level of detail are unprecedented. Seeing the telescope's new views of some familiar objects, from the photographed Carina Nebula to the planet Neptune, feels like putting on new glasses with a stronger prescription. Each image has created a stir, suggesting that, in the coming years, the telescope pictures will infiltrate the public subconscious just as thoroughly as Hubble's. While every scientist has their favorite astronomical body to image, one of the most anticipated avenues of research James Webb has opened up is the ability to explore what only infrared light can reveal. The history of the universe begins with a Big Bang, followed by a period of time during which the universe was hot and glowing. This initial hot period was when hydrogen and helium, the primordial elements that make up the early universe, were formed. As the universe expanded and cooled, its initial glow faded away about 380,000 years after the Big Bang, and the universe went totally dark. This period, known as the Cosmic Dark Ages, was when hydrogen and helium condensed. After 100 million to 200 million years, clouds of hydrogen and helium became so dense and hot that they began to undergo nuclear fusion, and the first stars were born. These stars were monsters, hundreds of times bigger than the Sun, shining white-hot, but they lived short lives. However, the universe plays tricks on us. The expansion of the universe stretched the short wavelength blue light emitted by the universe's first bright blue-white stars to longer wavelengths, green, yellow, orange, and red. Further stretching resulted in the light of the primordial stars reaching infrared, invisible to the human eye and even to the venerable Hubble Space Telescope. But it is precisely what the James Webb Space Telescope was designed to capture and render with its overwhelming power. The $10 billion machine has a spectacular mission to tell the story of our origins in the universe's distant past and relate it to other potential stories, perhaps of other creatures across the galaxy. To tell our story, the story of life on Earth, we must look back in time, connecting us to the story of the universe itself. As Carl Sagan famously noted, we are stardust aggregates of atoms forged in dying stars billions of years ago. The sources of our ancestral stuff were themselves forged by other dying stars in a cosmic bootstrap dance of creation and destruction that links all existing stars to the very first ones that emerged only about 100 million years after the Big Bang. Stars, like people and all kinds of life, have ancestry too. Just as we can build our family tree by looking at our ancestors, astronomers can reconstruct the evolution of stars in the universe by looking at the very first stars and how they evolved and exploded, giving rise to new stars that lived and died to generate a new crop of stars, and so on. To look back at the first stars is to do a kind of cosmic archaeology, unveiling the seeds that eventually made stars like the Sun and others possible, stars that can have a coterie of planets orbiting around them, with some in what we call a star's habitable zone. This connectivity between past and present is essential to understanding life in the universe. As James Webb looks back, it will also be looking at those planets that orbit stars in their habitable zones, aiming to map out the chemical composition of their atmospheres to seek molecules that are what we call biosignatures, those usually linked to the presence of life. In other words, this remarkable telescope will look both at the distant origins of life and at signs of life itself in other worlds, connecting life's origins with the possibility that we are not alone in the universe. In the quest to understand the first stars and galaxies that lit up the cosmos, James Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. However, Webb's findings were exciting in an uncomfortable sense. It discovered the existence of fully formed galaxies far earlier than should have been possible according to the so-called Standard Model of cosmology. According to the Standard Model, which is the basis for essentially all research in the field, there is a fixed and precise sequence of events that follow the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then, the force of gravity pulled together the stars into galaxies. However, the Webb data revealed that some very large galaxies formed really fast in too short a time, at least according to the Standard Model. This finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Explaining this excess may require substantial revisions to prevailing cosmological models, changes that could involve the first galaxies forming sooner, their stars shining brighter, or perhaps the nature of dark matter or dark energy being even more complex and mysterious than previously thought. While scientists scratch their heads and wonder if we need to rewrite cosmology altogether, James Webb continues to provide breathtaking new discoveries that could simply upend our understanding of the universe. According to new observations from James Webb, baby galaxies in the early universe ignited gas to trigger explosions of intense star formation. Many early galaxies, like the ones the James Webb Space Telescope detected, were rich with glowing gas, so bright that the gas itself could outshine stars emerging from within. These new findings reveal just how common such shimmering infant gassy galaxies were when the 13.8 billion-year-old universe was around only 2 billion years old. The team behind this research found that almost 90% of the galaxies had so-called extreme emission features, meaning they exhibited all that glowing gas. As research lead author and ARC Center for Excellence for All Sky Astrophysics in 3 Dimensions scientist Anu Gupta said in a statement, the stars in these young galaxies were remarkable, producing just the right amount of radiation to excite the surrounding gas. This gas, in turn, shone even brighter than the stars themselves. Until now, it was challenging to understand how these galaxies were able to accumulate so much gas, he said. The findings suggest that each of these galaxies had at least one close neighboring galaxy. The interaction between these galaxies would cause gas to cool and trigger an intense episode of star formation, resulting in this extreme emission feature. Interestingly, the discovery also confirms the assumptions of astronomers who suspected these extreme galaxies are indicators of intense interactions in the early universe. As team member and Curtin University researcher Ravi Jia said, "What's really exciting about this piece is that we see emission line similarities between the very first galaxies to galaxies that formed more recently and are easier to measure. This means we now have more ways to answer questions about the early universe, a period that is technically very hard to study," he said. In addition, this new conclusion is yet another example of how the James Webb Space Telescope was worth every penny of its $10 billion cost. Prior to this, astronomers simply hadn't been able to get a clear picture of star-forming galaxies that existed around 12 billion years ago. According to Gupta, the the data quality from the James Webb Space Telescope is simply exceptional. It is the data and resolution needed to see the neighbors and environment around early galaxies from when the universe was only 2 billion years old. With this detail, we were able to see a marked difference in the number of neighbors between galaxies with the extreme emission features and those without, he said. The data used by the team was collected as a part of the JWST Advanced Deep Extragalactic Survey, or JADE survey for short, the goal of which is to explore the earliest galaxies and open the door to future insights. As Gupta concluded, prior to James Webb, we could only really get a picture of really massive galaxies, most of which are in really dense clusters, making them harder to study with the technology available. Then we couldn't observe 95% of the galaxies we used in the study. The James Webb Space Telescope has revolutionized our work, he said. Of course, it should be noted that piercing the darkness to reveal the very first light is only the beginning. Billions of dollars and lifetimes of work have brought us to this historic moment as the science of James Webb begins. But all this is only the very first step on a journey of discovery that will take us from the first rays of cosmic dawn to the very ends of the universe. What mysteries and treasures await us along the way and in the untold depths of the sky? We're about to find out. What's interesting, however, even as James Webb is living up to the hype and its price tag by revolutionizing our understanding of the universe, Webb's predecessor, the Hubble telescope, is just showing that it's still in the game. The 33-year-old observatory, the Hubble Space Telescope, has just snapped a new view of a hazy spiral galaxy that once hosted a supernova explosion. The galaxy, formerly known as NGC 941, lies about 55 million light-years from Earth. Its spiral arms are bright but not very well defined, swirling outward from a bright core into a faint halo of dimmer gas. Hubble's Advanced Camera for Surveys, or ACS, observed the remnants of a stellar explosion within the galaxy. When some stars reached the end of their lives, they exploded in a brilliant burst called a supernova, which can briefly outshine the entire galaxy in which it sits. This particular supernova, known as SN 2005 AD, has since faded, leaving behind seeds for future star formation. Hubble's view captures the galaxy face-on, showcasing the realm's spiral structure and hazy surroundings. Using the Hubble data, SN 2005 AD was also studied as part of a larger initiative to understand the environments in which hydrogen-rich supernovae, known as Type II, occur following the rapid collapse of a massive star, according to a statement from the European Space Agency, or ESA. However, the initial discovery of supernova SN 2005 AD was made by an amateur astronomer named Kiichi Itagoki, who has discovered over 170 supernovae. As ESA officials said in a statement, this might raise the question of how an amateur astronomer could spot something like a supernova event before professional astronomers who have access to telescopes such as Hubble. The answer is, in part, that the detection of supernovae is a mixture of skill, facilities, and luck.